Our objective in 5.5 is to use properties of exponential and logarithmic functions of base a. That means a base that's any other number than e, the natural number. Differentiate and integrate with base a as well. So let's start out by talking about how we are going to define the exponential function of base a. So we've been working with the exponential function that's the natural exponential function of e to the x. Now we're going to be working with exponential functions of other bases like 5 to the x or 2 to the x, anything other than e. The way we're going to define a to the x is using the inverse property e to the natural log of a times x. We're going to define the logarithm of base a as 1 over natural log of a times natural log of x, or natural log of x over natural log of a. Some properties to remember about the exponential function and the log function of base a is they are inverses of each other. So y equals a to the x gives us also x equals log base a of y. Remember that logs are exponents, so the exponent is the log. The exponent is x, that equals the log. Also, the two inverse properties that we've been using, a to the log base a of x is just x, right? A to the log base a, I don't know if you can see that, a to the log base a, or log base a of a to the x is just x, right? Just x. So those two inverse properties right there, those are important to know for simplifying purposes. Simplifying is always a good idea because we'd like to have a simpler function for taking the derivative. Now, ultimately, you need to memorize the two derivatives, the derivative of a to the x and the derivative of log base a of x. So I'm going to write that down to start with. So first one, the derivative with respect to x of a to the x. Well, remember that you know the derivative of e to the x. Actually, let's write those down just as a recall sort of thing. So you know these two, the derivative with respect to x of e to the u, that's the easiest, e to the u, but use the chain rule du dx. You also know the derivative with respect to x of natural log of u. We write that as u prime over u. Okay, so let's go back up here and let's write it using the chain rule. The derivative with respect to x of a to the u. Well, just like e to the u, it has itself in it, so it is itself, but chain rule, and a constant multiple of natural log of the base. Why is that? I'll show you in a second. Other derivative you want to memorize, derivative with respect to x of log base a of u. Well, let's look back to the natural log of u prime over u. Well, this one is still u prime over u, but just like how we're multiplying by a constant of natural log of a here, we multiply by 1 over the constant of natural log of a here. Why are we putting it in the denominator here? Well, one helpful hint is remember how the exponential and logarithmic functions are inverses of each other? Well, what's the inverse of multiplying? That's right, dividing. Either way, memorize these. These are the derivatives you have to know. But keep in mind there are some similarities between, actually very, very similar between the e, the easiest, and the a, just the factor of natural log of a. Natural log of u prime over u, well, still u prime over u, but natural log of a. Now, I know you're dying to know why these formulas are as they are, so I'm going to show you. Let's start with the definition. A to the x is defined as e to the natural log of a of x. Think about if we do the derivative of the left side, so I'm going to write the derivative with respect to x of a to the x, and the derivative with respect to x of this side, natural log of a times x, all in the exponent. Okay, so all I did here was take the derivative of both sides. Otherwise, I rewrote what I had. Well, if I'm going to take the derivative of this side, I can think of this like e to the u. Well, the derivative of e to the u, we know what that is. And so I'll just make a little side note. The derivative of e to the u, that's the easiest, itself times du dx, chain rule. Okay, so we'll do this derivative, e to the u, e to all of that stuff, natural log of a, x, times the derivative of what's here. Well, natural log of a is a constant multiple as if it were 5. And what's the derivative of 5x? That's right, just 5. So the constant multiple, natural log of a. Well, using our inverse properties, this part right here, e natural log cancels out, the a comes down. So that part looks like this. A is now the base, x is left in the exponent, times natural log of a. So there you have it. The derivative with respect to x of a to the x is a to the x natural log of a. Of course, you have the chain rule, so we're calling this u, and we need to say times du dx. That's the chain rule. Let me show you why the other one is why it is, because I know you really want to know, as you should. Let's start with the definition of log base a of x. We're writing it as 1 over the natural log of a times the natural log of x. So we'll take the derivative of both sides. Okay, so you see what I did here is I just said d dx of both sides. Over here, well, 1 over natural log of a is just a constant multiple, so I'm going to pull that out, times the derivative with respect to x of natural log of x. Well, the derivative with respect to x of natural log of x is 1 over x times my constant multiple of 1 over natural log of a. And there you have it. The derivative with respect to x of log base a of x is 1 over x times the constant multiple of 1 over natural log of a. Now, normally we're going to have the chain rule. So if we call this u, how does this change? Not 1 over x, but u prime over u times 1 over natural log of a. So now that you feel better about how you know, let's get down to the bottom of things. You have to memorize these two derivatives. Let's go practice some. Number 1, differentiate 2 to the x. So I see this is of the form a to the x, and I've memorized the derivative of a to the x is itself times natural log of a. Well, the a is the base, it's 2, so in this problem, dy dx is 2 to the x natural log of 2, and that's it. If I have more than just x in the exponent, I could think of chain rule, but I could also think of simplifying this first. That's what I'm going to do here. I'm going to simplify first. Why? Because it makes it easier. 2 to the 3x is the same as saying 2 cubed to the x. Know your exponent properties to know why this is true. This is the same as saying 8 to the x. Know your exponential properties to know why this is true. Once we have that, it becomes exactly the same thing like we did in number 1. dy dx equals, I use my 8 to the x, natural log of 8, and I'm done. Simplify it first. Now, what if I can't simplify it first, or if it's a little bit more complicated than the simplifying I had in number 2, like in number 3? Well, then we don't worry about simplifying it first. Here we're going to use the chain rule. 2 to the 3x minus 5. It's an exponential function. The x is in the exponent. So I rewrite exactly what I see. I use the chain rule, so 2 to the 3x minus 5 times the derivative of the exponent times my extra constant natural log of the base. And there I have it. There is a derivative. Now it's not as clean as I'd like. Perhaps we use our log properties with this part and rewrite this as natural log of 2 cubed. What is natural log of 2 cubed? 8. So 2 to the 3x minus 5 times natural log of 8. This is probably the cleanest answer we should write. Let's practice some derivatives of logs. So I look up and I remember that the derivative with respect to x, and let's go ahead and remember it with the u's. Log base a of u prime over u times 1 over natural log of a. Memorized. Memorize this. So what do I have? dy dx is, the base is 5. So u prime, u is this guy, u prime is 1 over x times 1 over natural log of 5. Well, that's fine, but I can write that simpler. 1 over x natural log of 5. That's it. Memorize your derivatives. In this one, the u is actually more than just x, so I want to think of my chain rule. And be careful because when you don't see the base, it's base 10. This is equivalent to saying log base 10 of cosine x. Anytime you don't see a base, it's base 10. Unless it says ln, then it's base e. So we're going to do dy dx here. So we think to ourselves, u prime over u. U is cosine x, so u prime is negative sine x over u cosine x times 1 over natural log of the base, natural log of 10. We can simplify this a little bit, so let's do that. Negative tangent of x, because sine over cosine is tangent, and natural log of 10 in the denominator. Cool. So of course you're going to get log expressions that are going to be a little bit more complicated from time to time, in which case you want to remember really important is to expand. Sometimes expanding first is going to be the best option. So let's do that for this one, meaning I don't take the derivative yet. I break this up. This is a quotient, so I use subtraction. Log base 6 of 1 minus log base 6 of square root of x. But I can do even better here. The log of 1, whether it's the natural log or any other log with any other base of a log, is 0. So this is really negative of the log base 6 of, I'm going to write this as x to the 1/2 instead of square root of x. Why am I going to write it like that? Because I can move my exponent. So y is really negative 1/2 times log base 6 of x. How is this helpful? Because now I have a much simpler expression. Let's now take our derivative. dy dx, hang out the constant multiple, just hang it out, and we'll do the derivative of this guy. 1 over x times 1 over natural log of 6. There's our derivative, but of course we can simplify a little bit, so let's do it. Negative 1 over 2x natural log of 6 is a good answer. Or move this 2 to the exponent of the 6, and we can write it even simpler. Negative 1 over x natural log of 36. Pretty cool, right?